well. Welcome to the week 12 review of Math 2414. In this one, we're going to be finishing up a little bit more with some geometric series. Then we'll even get into some of our other series tests, such as the nth term test for divergence and the integral test. And we'll even talk a little bit about estimating remainders. I don't know if they talk very much about that. Of course, but I've seen a few problems on the homework, so we'll go ahead and touch on it. Alrighty, so let's just go ahead and start off. So let's recall the definition, or like what a geometric series looks like. If we have a series that's got like the sum from n equals 0 to infinity, a times r to the n, we call this a geometric series. And our geometric series test says that if r is smaller than 1, our series is convergent. And specifically, the magnitude of our radius should be smaller than 1. Moreover, if we have that this radius is smaller than 1, we can even find the sum, and the sum is equal to our first term a over 1 minus our radius. Right, that should all be review. So, I remember last week I gave you a few more difficult of our series, our geometric series problems. How are you feeling on those?
Okay.
You doing okay? All right. So if we had something like 2 times 3 to the n times 1/4 to the 2n, would you be able to find what that converges to?
So we'll take out, we'll try and make 1/4 to 2n and this make 1 as 2 roots.
All right. And how could we do that?
We can make it 1/4 to n squared.
Okay. So you're saying like take it, we've got n equals 0 to infinity, 2 times 3 to the n, and then 1/4 to the, which power again?
N squared.
Like this?
Or, actually, if you can, the squared to the n.
There we go. And then we can just go ahead and do 1/4 squared, right? And when we do 1/4 squared, we have 1 over 16, all to the n. And then we can combine everything with an exponent to the n. And now we have a nice 2 times 3 over 16 to the n. And we can really clearly see that our radius is what?
166.
Perfect, perfect. And then, of course, our first term, we just plug in n equals 0, and we get that 2 as our first term. So then our sum would be a over 1 minus r, or 2 over 1 minus 3 over 16, which is 2 over 13 over 16, which is 32 over 13. Yeah, seems like you did know what was going on. Nice work. Alrighty. So that's just a really brief review of some geometric series. Let's also touch briefly on some properties of convergent series. So let's say we have two series, and they both converge. Well, then what I can say is first off, if I take my first series, or either of my series, and I multiply it by a scalar, well, this is the same thing as I can move my scalar outside of my series, and I know that it converges. So multiplying by a scalar is a non-multiplier at all. I also know that I can actually take the sum or difference of both of my series, and I know that this should be equal to if I split it up. Moreover, because both of them converge, I can say that the sum or difference converges as well. So one quick example of this, if I let a sub n be like the sum from n equals 0 to infinity of 1/2 to the n, and b sub n be like the sum from n equals 0 to infinity of 1/3 to the n, well, both of these converge, right? So I can say, well, if I take 1/2 to the n and I multiply that by like 4 or something, well, then 4 times 1/2 to the n is going to converge as well. And I can also say, well, if I take 1/2 to the n and subtract 1/3 to the n, that's going to converge as well. And I can say that that sum is equal to the sum of 1/2 to the n minus the sum of 1/3. So that's just kind of what this is. It's pretty straightforward, right? All right. Okay. But these properties do not apply if one of our series would be divergent. Sound good? So if I took like 1/2 to the n and tried to add 2 to the n, well, I couldn't really say stuff about the sum because the 2 to the n is divergent. The 1/2 to the n is convergent. Our properties only work when our series are both convergent. Okay, and I think I threw in one more practice problem for you just so you could really get the idea of geometric series down completely. So go ahead and see if you can find the sum of that one. And that's a 1/3. Get it? No? Let's take a quick look. Where did you start?
I started by using the
Okay, and what did you do to do that?
So I'm getting 1/3 squared.
Okay, so 1/3 squared is 1/9. And we still have to do what next? Good, good. So what now?
And then I have A, like when we want to N. So
Okay,
that is 4E over 9.
good, good.
And then R, E, something.
Okay, perfect. Now what now?
Then divide 4E over 9 by 1 minus.
This is where you get your stuff. Okay, so everything is perfect up until this point. I'm guessing that these are maybe tripping up your algebra a bit.
Yeah.
So let's try and, let's go ahead and multiply by 9 over 9. Sound good? Well, on top, we have 9 canceling with a 9. On bottom, we distribute, we have 9 times 1. And then 9 times e over 9 is just e, right? And this is a perfectly good answer. Really, we just don't want to leave any fractions and fractions. So once we get rid of those fractions and fractions, this is good to go. And this would be our sum. Nice work. All right. So let's also talk briefly about a different kind of series. Have you heard of telescoping series? Yes. Okay. So telescoping series are a special kind of series where later terms are actually going to cancel out with a lot of the earlier terms. And they're actually one of the few kinds of series that we can find an exact sum for. So that's something that makes geometric series really special. We have a formula for the sum. And that's not going to be the case for a lot of our series. So let's say we have this series n squared plus n. Well, I can rewrite this by factoring the denominator. So this is now 1 over n times n plus 1. Well, I want to use partial fractions on this because I don't like having denominators that much. So I can write this as a over n plus b over n plus 1. And then I get that a times n plus 1 plus b times n should equal to 1, right? Now if I let n equal to 0, then I have a times 1 is equal to 1. So a is equal to 1. And if I let n equal to negative 1, then I have a times 0 plus b times negative 1 is equal to 1, so b is equal to negative 1, right? Alrighty. That makes my sum the sum from n equals 1 to infinity. Now I have 1 over n minus 1 over n plus 1, right? Now I'm just going to start writing out terms. I have 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5, right? And so on. Now you'll notice this negative 1/2 cancels out with my positive 1/2. This negative 1/3 cancels out with my positive 1/3. This negative 1/4 cancels out with my positive 1/4. So in general, after n terms, my sum, or I suppose I should use a different thing, after k terms, my sum from n equals 1 up to k of 1 over n minus 1 over n plus 1 is equal to 1 minus 1 over k plus 1, right? Yes.
I was watching the lecture last night.
Yeah, I messed that up last time. Yeah, sorry about that. But yes, audio is in fact on this time. Let's see, where was I? After k terms, we get that our sum is equal to 1 minus 1 over k plus 1. But then, of course, in our original, we had k as infinity. So then taking the limit as k goes to infinity of this sum, well, 1 over k plus 1 just goes to 0. So this limit is 0, right? Okay. Sorry?
If we have the infinity plus 1,
If we had infinity plus 1, that would still be infinity, right? You can't really cancel out your infinities. So if you have an infinity in there, probably just gonna have to say it diverges or you're unsure. Yeah, you can't really cancel out your infinities. So yeah, in this case, we could kind of keep these two things together because they were together originally, and our one was square present. So I will warn you that some series that look like they might be telescoping actually don't necessarily converge to a specific value. So as a quick example of that, let's do the sum from n equals 1 to infinity. We'll say the natural log of n over n plus 1. Sound good? Well, I can use my log rules and say, well, division in my log is equal to subtraction of two different times, right? So this is the natural log of n minus the natural log of n plus 1. Right? Well, if I start right, well, technically I need to start from, yeah, this will work. So then if I start writing out my terms, I have the natural log of 1 minus the natural log of 2 plus the natural log of 2 minus the natural log of 3 plus the natural log of 3 minus the natural log of 4 and so on, right? Well, what it looks like is it looks like I have natural log of 2 canceling with natural log of 2, 3 canceling with 3. So after k terms, what I have is the natural log of 1 minus the natural log of k, right? And the natural log of 1 is just 0. So I have the net minus the natural log of k. Right? The thing is, though, what's the limit as k goes to infinity in this case? All right? So k goes to infinity. What's the natural log? What's the limit of the natural log as it goes to infinity? It is infinity. So this actually goes to negative infinity. So this series, we actually say would probably diverge, because when we did our cancellations, we said, what we found is that this term, the last term that we didn't cancel, didn't necessarily have, it didn't go to 0 like we did in the first case. So in this case, our first example, the uncanceled term went to 0. In this example, the uncanceled term just keeps getting bigger. So that's the difference. Whenever you're working with the telescoping series, just make sure that your uncanceled terms are going to 0. Alrighty, there's a question.
Maybe some going to 0 in comparison to other. So the last question was going to is but let's say it's going to 0. That because passing.
Yeah. So in general, just like this, the last term that you didn't cancel, it should be decreasing. It should eventually go to 0 as you get larger some values. In this case, though, it wasn't. Yeah. Practice problem? There you go. How's it going? Get it? A bit longer? Sounds good. All right, let's go ahead and go over this. So what should we do first? Partial fractions, perfect. So we've got a over n plus b over n plus 3 should equal to 2 over n times n plus 3, right? So then a times n plus 3 plus b times n should equal to 2. So then if we let n equal to 0, then we have that 3a is equal to 2, so a is equal to 2 thirds, right? And then we can just look at the things with n power, so we know that an plus bn equals 0n, so a plus b equals 0. So a at 2 thirds plus b equals 0, so b is equal to negative 2 thirds, right? Okay. Which means right now we have the sum from n equals to 1 to infinity. I'm actually just going to go ahead and factor out 2 thirds. And now I'm left with 1 over n plus 1 over n plus 3. And I can do this because of my scalar multiplier, right? If it converges, then I basically ignore the scalar. That's all. Makes things a little easier, right? You're looking at this like, yeah. Yes, so pulling out the scalar at first can actually be really helpful. And now, let's just go ahead and, oh, and I believe this should actually be a negative, right?
Mhm.
Yes. All right, so let's just go ahead and start writing out terms. We now have 2/3 times 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6 plus 1 over 4 minus 1 over 7. And we'll do 1 more. Right, and what we notice is our negative 1/4 is going to cancel with a positive 1/4. Negative 1/5 is going to cancel with a positive 1/5. And then negative 1/6 is presumably going to cancel with the next term, right? So what I'm left with is 2/3 times 1 plus 1/2 plus 1/3 minus 1 over n plus 1 over k plus 3, right? Well, technically there should actually be a few more terms in here. So minus 1 over k plus 1 minus 1 over k plus 2 minus 1 over k plus 3. And that would be after k terms, right? But the thing is, letting k go to infinity, all of these go to 0, right? Which means I'm left with 2/3 times 1 plus 1/2 plus 1/3. Right? Realistically, you don't usually have to check super specifically that all of these go to 0. You can usually kind of just get a sense for it. Are your terms all decreasing? Yes. Okay, then they'll all go to 0. So like 1 over n is always decreasing, 1 over n plus 2 is always decreasing. So any of those terms are going to go to 0. So often it's not actually great to do a super formal check because it's easy, just like get lost in, oh, which terms are left. So as long as all of these things are individually decreasing, you know that your later terms are going to go to 0. Make sense? That's just a little easier. And now we just need to finish up doing some nice little algebra. 1/2 plus 1/3 is 5 over 6, plus 1 is 11 over 6. We've got 2/3 times 11 over 6, which gets us 1/3 when we simplify, so we are left with 11 over 9 as our solution. Sound good? Perfect, perfect. All right. Let's do one quick example. And this one is going to be a really famous sum, or just 1 over. Sound good? Now you've seen this one before, right? Possibly. Do you know if it converges or diverges? Yeah, so this is actually a p-series test. A p-series with p equal to 1, right? And when p is equal to 1, does it converge or diverge? So we diverge, right? You do diverge. Let's see if we can show it though without using the p-series test. And then later on we'll prove the p-series test using the Sound good? All right. So I'm just going to start writing out terms for this. We have first 1, then we have plus 1/2, plus 1/3, right? Plus 1/4, plus 1/5, plus 1/6, plus 1/7, plus 1/8, and so on, right? Well, what I'm going to do now is I'm going to say, what if I took my 1? So I know that my 1 is bigger than 1/2, right? So I know that this overall series should be bigger than another series that I'm going to define by taking my 1 and turning it into 1/2. My 1/2 is going to stay 1/2. I know that 1/3 is bigger than 1/4, right? So I'm going to take my 1/3 and my 1/4. And 1/4 plus 1/4 is 1/2, right? But since 1/3 is bigger than a fourth, I know that 1/3 plus 1/4 should be larger than 1/2, right? So I'm going to take these two and combine them and say this is plus 1/2. And I know that 1/3 plus 1/4 should be bigger than, right? Now I'm going to do the same thing with the next 4 terms, because I know that 4 times 1/8 is 1/2, right? But then each of these 3 things are bigger than it, right? Which means that 4 times 1/8, which is 1/2, should be smaller than these. And I can keep making groups of 1/2 like this as many times as I want. Which means that I have a sum from n equals 1 to 1 infinity of 1 over n, then should be bigger than the sum from n equals 1 to infinity of just 1/2. Right? Because I just have 1/2, 1/2, 1/2, 1/2, adding them all up. But then if I add up a half as many times as I like, does that diverge or converge? Right, it would diverge, because I would say, well, if it converges, then it's going to have a biggest value, right? But then I just take whatever my biggest value is, and I say, well, I'm going to add as many more 1/2s until I pass it. So then I can't have a biggest value, so it has to diverge. But then because this is a smaller series and it diverges, we know that the bigger series would have to diverge as well. Right? And that is the proof. That makes sense?
That's what I want to write. So why did you say that there's why did you say something?
So what I was trying to do is I was trying to establish this inequality here. I'm trying to say that my 1 over n series is always bigger than something like just 1/2. Because I know that this diverges. So if I can say that this inequality is true, then I know that because this diverges, the bigger series also has to diverge.
Oh, like when you previously, I can't remember what we did, but like if one part of something really divergent.
Maybe improper integrals?
Yeah. If one part.
Yeah, so improper integrals and series are actually pretty closely related. One thing to think about it, though, is a divergent series has to go to infinity. So something larger than infinity is just infinity, right? Yeah. Okay, does this make sense now? Perfect, perfect. All right, let's talk then about the nth term test. And this is a theorem. It's called the nth term test for divergence. And what it says is, let's say we have a sum from n equals 1 to infinity of some series a sub n. Well, we can say that this series diverges if we have the limit as n goes to infinity of our sequence a sub n is not equal to 0. If the limit of the sequence is equal to 0, we can say nothing about whether it converges or diverges. So let's do a quick example. Let's say we have a sum from n equals 1 to infinity of 1 plus 1 over n to the n. Well, let's apply our nth term test. Sound good? Okay. Well, by the nth term test, we need to say what the limit as n goes to infinity of 1 plus 1 over n to the n's. Do you happen to recognize this limit? It is a special limit. We actually say that this limit is e. So this is a special limit. I kind of wanted to throw it into this to remind you. You might see it again sometime soon. So when you see things kind of similar to this, you might think, maybe there's going to be an e. But regardless, is e larger than 0 or not? Is it equal to 0, I guess? It is not equal to 0. So we say that our series n equals 1 to infinity, 1 plus 1 over n to the n diverges by the nth term test. And you might also hear this test called the divergence test. It has a few different names. All right, so now let's actually take the divergence test, or the nth term test, and apply it to our nice 1 over n. So what should I do in this case?
We should find something that
I just want to apply my nth term test to it. So, okay, so in the nth term test, all we do is we take the sequence, place it in, and we take the limit as n goes to infinity of that sequence. So what's the limit as n goes to infinity of 1 over n? It is 0. And what does that tell us? No. That is the trap that everyone will fall into, which is why I want to make this very clear. If we get that the limit is equal to 0, we know nothing. So this is the nth term test for divergence. It will only tell us if a series diverges. It will not tell us every time a series diverges. It will never tell us that a series converges. If you ever say you're using the nth term test to show that a series converges, you are doing something very, very wrong. So, because this limit is equal to 0, we know absolutely nothing. We cannot say it converges. We cannot say it diverges. We need to use a different test. In other words, we say that the nth term test fails. Because it just doesn't really tell us any information. The reason the nth term test is useful, though, even if it's maybe not quite as effective as some other tests, is because it's really easy to do, right? We can just pretty quickly take the limit. So that's why it's a good test to apply first, because it can really quickly say, oh, this series will diverge. And then in most cases, it's going to tell you nothing. But you spent so little time on it anyway that it was pretty easy. Alrighty. Let's talk then about a more powerful test, the integral test. Have you covered this one? Good, good. So the integral test is a really big one. So let's say we have some function f of x, such that whenever we plug in an integer n, we happen to get exactly our sequence a sub n. And we have that our function f of x is positive, continuous, and decreasing. So these are three conditions we need in order for our integral test to apply. Usually, you'll get the decreasing from just checking your nth term test, because if it's positive and the limit goes to 0, you know that it would then be decreasing after a certain point. Continuous is usually fairly easy to check as well, so is positive. So these are the preconditions. Well then, we say that the sum from n equals 1 to infinity of a sub n is dependent then on the integral. So we can say that the sum converges if and only if the improper integral from 1 to infinity of f of x dx converges. And of course, we can say the exact same thing as far as diverging as well. So your series is going to diverge if the integral diverges. Your series is going to converge if the integral converges. Yes?
Okay. Follow-up question to the previous question, to the previous example. What test would we have used, or we're going to use that test? Instead of the,
Or
another
1 over n?
Hmm.
Yeah, so that is actually the p-series test usually, which is a very specific instance of the integral test. So what I'm going to do is I'm going to actually do it as an example right now. So let's say we have a series, sum from n equals 1 to infinity. This time though, I'm going to say it's 1 over n to the power of some p, where p is a real number. Sound good? Well then I'm going to define my function f of x. And my function f of x is just going to be 1 over x to the p. Sound good? Okay. Well, first things first, I need to find my integral, right? Technically speaking, I would need to check that f of x is positive, continuous, and decreasing. In this case, x to the p is always going to be positive when x is positive. It's always continuous when x is larger than 0. Technically, it only is decreasing when p is, let's see, sorry? Yeah, so technically p would it would only be decreasing if p were, I want to say actually bigger than 0. So I'm just going to say it's positive, continuous, and decreasing for p larger than 0. Right. Yeah, so usually if it's continuous, it's just the same methods you use to find continuity for functions normally. So like 1 over x to the p, that's just a polynomial, right? So we just need to make sure we're not dividing by 0. And the only situation we're dividing by 0 is if x is equal to 0. But because we're taking the integral from 1 to infinity, x equals 0 isn't even considered in that domain, so we're continuous on it. Sound good? All right. So I'm going to break this problem into 2 chunks. First off, if p is smaller than or equal to 0, well then I have 1 over n to the p would then be 1 over n to the minus p. And since p is smaller than or equal to 0, I know that minus p is bigger than or equal to 0. Right? So into the something, so then this is into the something greater than 0, which then is of course bigger than, as n goes to infinity, this goes to infinity as well, right? So if p is smaller than or equal to 0, it fails the indeterminants, right? We diverge by the indeterminants. Does that make sense? I know I went through it kind of quickly and loosely. Yeah. So I know that my integral test is only going to apply where f is positive, continuous, and decreasing. And that only occurs when p is bigger than or equal to 0. So I'm only going to apply the integral test when p is bigger than 0. Which means I need to apply a different test when p is smaller than or equal to 0. If p is smaller than or equal to 0, well, I have 1 over n to the p, which is n to the negative p. But since p is less than or equal to 0, I know that negative p should be greater than or equal to 0, right? Which means that n to the negative p is the same as n to something bigger than 0. Well, if I take the limit as n goes to infinity of n to the power of something greater than or equal to 0, this is either going to be infinity, or potentially if p is equal to 0, it could go to 1. So I either have when p is equal to 0, I have n to the 0, which is 1, or regardless, the limit as n goes to infinity of 1 is equal to 1, which isn't 0, right? And if p is larger than 0, well then I have that n to the p is bigger than n to the 0, which is 1. So because I have a smaller thing that diverges, then anything bigger should also diverge, right? So again, this one will diverge as well. Sound good? Okay. Now I'm going to apply the integral test when p is greater than 0. Because now I've checked that my function is positive, continuous, and decreasing, right? Okay. Well then I need to take the indefinite integral from 1 to infinity of 1 over x to the p, right? Well, there are a couple of different situations that can happen. I'm going to break this up into 3 situations. First off, I'm going to say when p is bigger than 0 but less than 1. Sound good? My second one is going to be when p is equal to 1. My third one is going to be when p is bigger than 1. Well, if I have p equal to 1, well then I have the integral of 1 over x. The integral of 1 over x is what? Not quite. That would be just x. But since it's 1 over x, we use natural log, right? Okay. If p is smaller than 1, then I can use my power rule. I'm going to rewrite this as x to the minus p. So then I have increase my power by 1. Negative p plus 1 is the same as 1 minus p. And then I need to multiply by the reciprocal of my power, right? And technically, I actually have the same thing when p is greater than 1. But you'll remember in each of these cases, what I'm going to need to do is I'm going to evaluate the limit as n goes to infinity, or as x goes to infinity, right? Well, in this case, I have x to a power bigger than 0, right? Well, infinity to a power larger than 0, that's still infinity, right? So I end up with infinity for 0 smaller than p smaller than 1. Now, what's the natural log of infinity? 0. Sorry? Not 0. It is infinity, yeah. Remember the graph of natural log? Looks kind of like this, and it just keeps going upwards. And that happens when p is equal to 1. The last case, though, we have x to the 1 minus p where p is larger than 1. So 1 minus p should be smaller than 1, so we have x to a negative exponent. And when you have a negative exponent, that's like 1 over x to a positive exponent. So 1 over infinity to a positive exponent, that's going to go to 0, right? So we have 0 minus 1 over 1 minus p times 1 to the 1 minus p. Now 1 to the 1 minus p is still 1, so we have 0 minus 1 over 1 minus p, which is 1 over p minus 1. Now importantly, this is a finite number. So when p is bigger than 1, we have that our integral converges, right? And what does our integral test say? If our integral converges, then our series should converge as well, right? Which means that because our integral converged for p bigger than 1, our series should converge for p is bigger than 1. We also showed that if p was equal to 1, between 0 and 1, and smaller than or equal to 0, so basically anything less than or equal to 1, it would diverge. And this is our p series test. Make sense? Ooh, cool. Pretty exciting, huh? Yeah. Yeah. Good stuff. All right, practice problems. Sound good? First off, we'll do the sum from n equals to 1, yes, 1 to infinity, natural log of n over n. Second, we'll do that one. I'll give you a few minutes to work through that. All right. We are running a little short on time, so let's just run over these. Sound good? All right. So our first one, we're going to apply the integral test. We're going to let f of x equal to the natural log of x divided by x. Now, when x is larger than 1, we have that it's positive, since natural log of x is positive and x is positive. We have that it's continuous, because the only places it would be discontinuous are where x is smaller than or equal to 0. And we have that it's decreasing because x is like a faster growing function than natural log of x. So that's decreasing as well. Which means we can apply our integral test. So we take the integral from 1 to infinity with the natural log of x divided by x. And to do this, we take a nice u substitution. I'm going to let u equal to the natural log of x. So then what is du? Perfect, perfect, which means I now have the integral of u du, which is 1/2 u squared from x equals 1 to x equals infinity. So I'm going to rewrite this as the limit as b goes to infinity of 1/2 times the natural log of x squared from 1 to b. And of course, the limit as natural log goes to infinity is infinity, right? So when I square it, it's still going to be infinity. So this one diverges. Specifically, it diverges by the integral test. And again, because my integral diverges, my series diverges as well. Good on that one? Did you get that one? Perfect, perfect. And this one, a little different. Alrighty. So again, I'm going to let my f of x just be equal to replace all the n's, right? Well, x is continuous everywhere. E to the x is continuous everywhere. X squared is continuous everywhere. I can mash them all together into one nice function. That should be continuous everywhere, right? I also know that x is positive and e is always positive. So x times e to anything is always positive. Were you getting thrown off by the negative in the exponent? Yeah. The thing to remember is e to any power is always positive, even if the power is negative. Also, when I have e to the negative x, that's decreasing. In fact, the graph of e to the negative x looks kind of like this. So e to the negative x squared is kind of just going to do that a little faster. So we can see it's also decreasing. Even if we multiply it by x, the e to the negative x squared is just decreasing so much faster than the x is increasing. It's technically decreasing as well. If you wanted to do a formal proof, you could do like, well, you could show that f of x plus 1 was always smaller than f of x. And you would do that just by plugging in like x plus 1 and x, canceling everything until you got a statement like 0 is less than 1 or something like that, which is just true. And you'd be like, oh, well, this statement is true, so everything else that I said would be true as well. You look a little confused. We'll go ahead and do this a little more clearly. So if I plug in x plus 1, then I have x plus 1 e to the negative x plus 1 squared, right? Which is x plus 1 times e to the negative, or to the negative x squared plus 2x plus 1. And I'm going to claim that this is smaller than x e to the negative x squared. Sound good? Okay. Well, here I have x, well, let's see. What's the best way to do this? This one's a little trickier because of this plus 1 right here. But what we can do, let's see. we'll go ahead and distribute. We have x plus 1, and I'm going to distribute my negative and actually break everything apart. So e to the negative x squared, e to the negative 2x, e to the negative 1. Right? Now I can cancel out an e to the negative x squared on both sides. So then my claim is now x plus 1 times e to the negative 2x, e to the negative 1 is smaller than x. And also because I'm only integrating on the interval from 1 to infinity, I know that x should be bigger than 1, right? Okay. Well, let's see. I know that x is smaller than x plus 1, right? So I'm actually going to just work with this. Let's see, can I do this actually? No, I don't think that's enough. Never mind. I'm not going to work with that. So now I have x e to the negative 2x, e to the negative first, plus e to the negative 2x, e to the negative first is smaller than x. Now if I divide all the sides by an x, I have a 1 here, I have divided by x here, and then this x cancels, right? Well, what I happen to know is that e to the negative 2x times e to the negative first, as I let x go to infinity, this is going to get really small, right? Similarly, this is also going to get really small. In fact, I can really just see, because x is bigger than 1, whoa there. This is always going to be less than or equal to e to the negative 2x, e to the negative first. Which means that all of this is really going to be small. All of this left-hand side is really going to be smaller than 2 e to the negative x, 2 times e to the negative first. And e to the negative 1 is just 1 over e. And 2 over e is still less than 1. So because that's less than 1, it's a true statement for all of the x values bigger than 1. So then I've showed, oh, f of x plus 1 is always smaller than f of x for all of my x values. So it's a decreasing function. And that's like a really formal way of doing it. But we showed that it's positive, continuous, decreasing, so we can apply the integral test, right? All right, let's do some integration. Any ideas as to how I can do it? And what should you be? Not quite. I actually want it to just be negative x squared. So then what's dx? So then in my problem, I have an x dx. So I have that, oops, that should be a du right there. So then I have that negative 1/2 du is equal to that x dx that I want to replace, right? So then I'm left with the integral from x equals 1 to x equals infinity of, suddenly I have e to the u du, and the integral of e to the u is what? It is, the integral is just e to the u, which is, in this case, e to the negative x squared from x equals 1 to x equals infinity, right? Now what is e to the negative infinity? Oh, you're right. I completely forgot about that. There we go. There's the negative 1/2. Thank you for reminding me. Good catch. Right? E to the negative infinity is 0. So you have 0 minus negative 1/2 e to the negative 1, which is 1 over 2e, which specifically is a finite number, right? So this integral converges. So we say that the sum from n equals 1 to infinity, n e to the negative n squared also converges. One last thing to note, we cannot say that the sum of this series is 1 over 2e. The value of the integral is not the same as the sum. That's one thing to remember. The value of the integral is not the same as the sum. It's going to be pretty close, and if we had time, we'd actually talk a little about how you can use the integral to kind of estimate the sum, but we're out of time, and I don't think they really talk too much about it in your course, do they?
I think in they talked about something, someone else said about it, but it's a homework, and instead, is that what the remainder is about?
Yeah, so I'll just really quick give you the formula. So we can say that the sum from k equals 1, or from n equals 1 to infinity, of some series a sub n, we're going to break that down into 2 parts. We're going to say Sn plus Rn, where S is equal to the sum after n terms. And Sn is the sum after n terms, and Rn is the remainder. Which means that S, the actual sum, is your sum after n terms plus your remainder left to be added. Well then, we have a nice formula based on the integral, and that says that the integral from n plus 1 to infinity of our function corresponding to our sequence is smaller than or equal to our remainder after n terms, which is smaller than or equal to this integral here. So basically, your overall remainder is in between the integral from n plus 1 terms and the integral after n terms. And that's just the formula for how you can maybe estimate the remainder. But you can't really calculate the remainder exactly, because otherwise you'd be able to calculate the sum exactly. And calculating the sum exactly is often really, really hard. So,
yeah, there's just 2 questions on the conference.
so that's the formula if you want. Yeah. Other than that, thanks for coming in, and that's all I got for you today.